So for this topic, we're going to be talking about the family of functions and the transformation of any one of those families of functions. So you may or may not be familiar with all of these, but I'm going to go ahead and throw up the most common ones. So we have y equals to x, and the graph of y equals to x is just a line. So let's go ahead and put that there. Woo! Just a straight line, could be positive or negative slope. There we go. And I'm doing these all for the simplest versions, and then we'll talk about the other things. What if this had a negative slope? So that's y equals x. Then we also have y equals x squared, which is a parabola. So it looks like that. We also have y equals x cubed, which is kind of this snaky looking thing right here. We've got y equals 1 over x. This one's interesting because it sort of splits. So we've got something goes like that, goes like this. We have y equals the absolute value of x. Notice this one's pretty cool because if I throw the graph here, woo, it's like a V. So notice the parabola is nice and smooth, but the absolute value is V shape. Then we've also got y equals sine of x. This one starts right here at the origin and then just snakes its way up and down like that. And of course it continues in both directions. And then we finally have y equals cosine of x. This one starts up here and then snakes its way down, just like sine does. So we have this family of functions here. Now, what's cool about all of these is that there are things you can do to them to move them around. You can stretch them out, you can shrink them, and of course you can do that depending on which axis you're talking about. You can flip them upside down, and there's all sorts of transformations you can do. So just for example, say if I take x squared, everybody's favorite. Regular old x squared looks like this, just like I have over there. Now, if I wanted to move the whole graph up or down, what I could do is I could say subtract 2. So now this whole graph, all the points on it, would move down 2 units like this. And so I've shifted it down like that. I could make this a plus 2. Then that would go 1, 2, and everything would be up 2 units. Okay, so what are some other things I can do? Well, I can move it left and right. I can do a shift, and that causes every point to move either to the left or to the right. Now, the one thing that's interesting about shifts is that you're actually going to do the opposite sign of which direction you're trying to go. So it's a little tricky. But let's say I wanted to do y equals x minus 3 squared. Well, now what happens is instead of the graph just being here like it is in our original thing, I've got x minus 3. So the whole graph moves to the right 3 times. And again, these things are true for all of these functions. If I add or subtract a number at the very end after the function, ends, you could say, after your variables and everything, that moves the whole graph up or down. If I add or subtract a number inside, right next to the x before anything else happens, that shifts everything left and right. And this is going to be true for all these functions. Now, one other thing I can do is I can also stretch or shrink things. So let's look at this guy right here. Let's say I wanted to make this a lot skinnier. Well, I could multiply in front here by some number. And since I want to make this skinnier, what I'll do is let's just say 7. Fairly big. What's going to happen is now where y would have been 1, it's going to be 7. Where y would have been 3, it's going to be 21. And so everything is getting shifted way up. So this makes it really skinny, maybe something like this. Likewise, I could also shrink the graph. So let's say, or compress it. Let's say instead of stretching up like this, I wanted to shrink it. So I'm going to get rid of that 7. Let's say instead I multiplied here by 1/3. So notice some value less than 1, a fraction. Well, now I'm reducing how large these y's get. So where this whole thing would have been 3, now it's going to be 1, right? So this could like knock down to here. Where it's going to be 1, it's going to be a third, and so on. And so now I've squished the graph, and it's a lot smaller now, or at least it's, flatter. Again, this will happen to any of these. If you multiply right in front of the whole function by a number greater than 1, that stretches it up like this. If you multiply by a fractional number, that squishes it down like this. Now, let's say you wanted to flip this upside down, right? Well, that's pretty straightforward. For my original x minus 3, I could just, I'm going to write it here, and then I'll put the function right next to it. This right here would be negative x minus 3 squared. So if I multiply by negative numbers now, every y value that would have been positive gets flipped. And for some of these other graphs, like say the x cubed function here, if I had multiplied that by a negative 1, all the positive ones would flip over, but all the negative ones, negative times negative is positive, would flip up as well. So I can do negative numbers for any of these values I did before. So if I had done negative 7 instead of positive 7, this would be going down. It would still get all stretched out, but it'd be going down that way. Likewise, if I did negative 7, or negative a third, instead of just a third here, the same sort of compression would happen, but it would also flip upside down, like that. And this is true for all these functions. They all behave this way. And so it's pretty nice. It's pretty cool, because it happens to all of them. And so that was a discussion on the families of functions and how you can transform, stretch, squish, compress, shift, move them around, and do all sorts of cool stuff with them.